All right, you have no way of knowing this right now, but I am playing a very exciting of nap roulette, which is where we see what happens first. I finish the notes or Skylar wakes up. So this could be very exciting. We literally just finished talking about identifying the solubility of compounds in double replacement reactions, therefore allowing us to determine whether or not a reaction happened. We're going to use this information and the solubility rules to write what are called net ionic equations. And what net ionic equations do is they eliminate the fluff, if you will, from these double replacement reactions and also from single replacement reactions. And by eliminating the fluff, and I'll explain what the fluff is here in a second, we are left with just the ions that actually participate in the chemical reaction. So our goal is to eliminate what are called the spectator ions from single and double replacement reactions, so leave just the parts involved in the chemical reaction. Now when you think of a spectator, you are probably imagining someone watching a sporting event, which none of us are doing right now because, well, obvious current events. And I like to think of them as people who, no matter how much they shout at the ref, don't affect the outcome of the game. Okay, so they are spectators, they are watching, they don't change, they are not affected by the chemical reaction at hand. So a spectator ion, here's how you're going to identify a spectator ion, is an ion that remains in the aqueous phase and does not undergo a chemical change. All right, even if there's a chemical change happening around it. So we're going to take these double and single replacement reactions and we're going to boil them down to the most important parts, and those are called the net ionic equations. Net, not net like basketball hoop net, I think more net like net versus gross income. Gross is the money that you think you make, but that's before the government takes their cut. Net is the amount of money that actually makes it into your bank account, which is considerably less, which makes me cry on a monthly basis. But anyway, so let's dive into this. In order to take a double or a single replacement reaction and turn it into a net ionic equation, you need to do the following things, and I'm going to walk you through all of these. First, complete the chemical reaction and predict the solubility of products. You should be very good at that by this point. Next, you're going to write the total ionic equation by ionizing aqueous reactants and products. Very important word here is aqueous. Okay, we are only going to ionize aqueous things. Next, we will eliminate the spectator ions, and I'll show you how to find them. And then finally, you're going to rewrite the remaining pieces as the net ionic equation. So let's dive into this. This will make a lot more sense when you actually see it in action. So here we have a double replacement reaction. I know that because I have two compounds, sodium chromate and iron 2 nitrate. So remember, these are two separate solutions and I'm going to mix together, hoping that something happens. So I will produce sodium nitrate, and my other product would be iron 2 chromate, so FeCrO4. I'll go back and balance this reaction, which will just require a 2 right there. Next, I need to evaluate the solubility of all of these reactants and products. Remember, we have some alwayses that we want to keep an eye out for. So sodium is an always. So that was working. Without hesitation, I know that sodium chromate is going to be aqueous. Nitrate is another alwayses. All right, so there's another aqueous compound. So these are two homogeneous mixtures. When I mix them together, sodium nitrate is another aqueous compound, so this will never actually form. It will just be a bunch of ions floating around. Iron chromate, however, all right, there's chromate, it's typically insoluble. Iron is not an exception, so this will form a solid compound. Okay, so you should be very good at that at this point. Okay, so that's number 1 completed. Next, we need to write the total ionic equation by ionizing aqueous reactants and products. We talked about ionizing in our notes previously. Ionization, remember, is just when a compound breaks down into its ions. This is a physical change. It is not chemical. It is reversible. Okay, so all I'm going to do is separate ions, keeping in mind and keeping track of quantities of ions. Okay, so for instance, and by the way, I'm only going to do this for aqueous reactants and products. So here's one right here. Sodium chromate is an aqueous reactant. So I'm going to ionize this compound into its ions, or disassociate this compound into its ions. So I'm going to have 2 sodium atoms, 2 Na1+, and those ions are aqueous. Anytime you have an ion, it is aqueous. Like, just no hesitation there whatsoever. I also have a chromate, CrO4 2- that is also going to be aqueous. Okay, so I've taken this compound, ionized it into its pieces. This is a better representation of what it actually looks like in solution. I'll do the same thing with iron 2 nitrate rather, which is another aqueous compound. So it is just a bunch of iron and nitrate ions floating around in solution. So Fe2+ aqueous, and then note 2 NO3 1- ions. So this is what it looks like at the very beginning of the reaction before anything has happened. Okay, let's look at what it looks like on the products side. So one of my things is still aqueous, so this sodium nitrate. So I'm going to ionize this. So 2 Na1+ that are aqueous, and 2, this 2 applies to the nitrate as well, 2 nitrates that are also aqueous. Okay. Now I get to my last product, which is this iron 2 chromate. It is not aqueous, it is solid. Okay? If this said gas or even liquid, I would treat it the exact same way as I'm going to now. I am going to write it exactly the same way. I'm not going to change it at all. Alright, it's just FeCrO4 solid. The reason being is it's not aqueous. Okay, so it isn't a bunch of ions floating around in solution. It is a solid crystal precipitate that has fallen out of solution. Okay, so this is what is referred to as the total ionic equation. This is everything floating around in solution before the reaction happens and then after the reaction happens. Okay, so this is kind of like the gross. This is everything. This is a lot of information. And what I'm going to figure out is I don't need all of this information because some of it isn't doing a whole lot. So what I'm going to do is find what are called these spectator ions. So remember, these are the guys that are watching, they're not participating, they're just shouting at the ref and hoping to make a difference, but we all know it doesn't. Okay. So in order to find the spectator ions, I want to find something that does not change as it crosses the reaction arrow over into the products side. Sodium is an excellent example of this. On the reactant side, I have 2 Na1+ aqueous, and look over here. On the right, I have 2 Na1+ aqueous all over again. Okay, this is a spectator ion. It does not change. Chromate is a terrible example of a spectator ion. In fact, it's not a spectator ion. Here, on the reactant side, it's CrO4 2- aqueous. On the product side, it is part of a solid compound. It undergoes something chemical. So, yes, spectator ion. No, not a spectator ion. So I need to find all the spectators and eliminate them. Sodium is one. The other would be nitrate. Nitrate is the other spectator that does not undergo a chemical change. Now, if you have done your job correctly up to this point, in other words, you have balanced your reaction and kept track of all of your ions, you are essentially done. Because step 4 is just to rewrite everything that's left over as the net ionic equation. And if you've done your job correctly, it should already be balanced. So, I'm going to leave out the spectators, and I am left with CrO4 2- aqueous plus Fe2+ aqueous gives me a product of iron 2 chromate solid. Alright, that is your net ionic equation. That is the chemistry that is actually happening in the beaker, and it has eliminated all of the fluff or all the spectators that don't actually participate in the chemistry. Okay, so that's an example with a double replacement reaction. It can be done with a single replacement reaction as well. So here we have a metal replacement. The magnesium is going to try and kick out the cobalt. Magnesium is more reactive than cobalt, so this will happen. We're going to make MgCl2, and we're also going to make cobalt. Okay, so if I evaluate, oh sure, let's balance it first. So we're going to need 2 of those, and 3 of those, and 3 of those, and 2 of those, and now we can evaluate solubility. Remember, the solubility rules only work for compounds. You already know the solubility of elements. Magnesium and cobalt are both black lettered on the periodic table, so they are going to be solids. Okay, and then cobalt chloride and magnesium chloride, both are chloride containing. I can check here. Cool. Cobalt nor magnesium are exceptions, so both of those compounds will be aqueous. Okay, looks a little bit different than a double replacement reaction, as it should, but I can go through the same process of writing out a total in a net ionic equation. So remember, the way we go from the balanced chemical equation to the total ionic equation is by ionizing anything that's aqueous, just the aqueous things. So for instance, this 3 magnesiums, I'm going to leave them exactly the same. I'm going to rewrite them. 3 solid magnesiums. Okay, I'm not going to change them. I'm not going to throw a charge on there. That would turn it into an ion, which would make it not solid. I'm going to write it exactly the way that it is. Okay, because if I take a piece of magnesium and I throw it into water, it does not dissolve. It might react with the water, but that's a whole different thing. But now we have an aqueous compound that we can dissolve. So this is going to be fun. We've got 2 cobalt ions, 2 CO3 plus ions that are aqueous, and then 6, count them, 6 chloride ions that are also aqueous. So that's everything on my reactant side. I'm going to ionize one of my products as well. So we've got 3 Mg2 pluses that are aqueous and 6 Cl1 minuses that are aqueous. Hopefully you're already finding a spectator. And then this will not change, 2 CO solids. Okay. This time we only have 1 spectator ion, and it's these 6 chlorides. Okay. Magnesium starts as a solid and in its elemental state and ends in its ion in its dissolved aqueous state. Cobalt goes through the exact opposite process. You will learn at some point that this is a redox reaction where we have an exchange of electrons and changing oxidation states, but we'll get there later. So I'm done. All I need to do now is just rewrite my net ionic equation. The mistake that I see most often is people just decide, hey, I'm going to just throw a charge on here because I want to. Don't do that. That kind of defeats the whole purpose. Okay, so there's my completed net ionic equation for a single replacement reaction, which just shows the elements that are gaining and losing electrons. Okay, not the case with my double replacement reaction. We do not have a redox. We do not have an exchange of electrons. This is just the formation of a solid. Okay, I've got a couple more examples that we can do quickly, hopefully. Because again, playing nap roulette, and it sounds like I'm losing. Okay, so real quick, here's another double replacement reaction. We would make manganese 3 phosphate, so that would just be MnPO4, and then lithium sulfate Li2SO4. This should be super fun to balance. We're going to need 2 of those, 3 of those, which gives me that, and actually that really wasn't bad. Okay, cool. So we need 2 right there. Next thing you need to do is assess solubility. We're going to pause so I can deal with nap roulette. Okay, I think I bought myself maybe 5 more minutes. We'll see. Hopefully you have your solubility rules next to you and you can see that sulfates are almost always aqueous. Manganese is not an exception to that. Phosphates are usually insoluble or solids, but lithium is a 1A metal, so that's an exception to that rule. So that will make that aqueous. Okay. Lithium sulfate. Sulfates are usually aqueous. Lithium not an exception, so that will be aqueous. Manganese 3-phosphate, on the other hand, is most definitely going to be solid. I'm trying to think of a metaphor to explain to you just how terrified I am of my kid waking up, but I'm coming up short. I did just have to turn on a sound machine that emulates a purring cat. So that's weird, but it works. So we're going to take this double replacement reaction and we are going to boil it down to the most important parts. We're going to eliminate the spectators, eliminate the fluff, and just be left with the net ionic equation. So first, total ionic equation. So this would turn into 2 manganese 3 pluses that are aqueous, and then 3 sulfates that are also aqueous. We would have 6 lithium ions, and then 2 phosphates on the reactant side. On the product side, here's my solid product, which means that this double replacement reaction does happen, it undergoes a chemical change. So I'm going to leave that exactly the same, 2 MnPO4 solids, but then I would ionize or dissociate this lithium sulfate compound. So I have 6 lithiums and 3 SO4 2 minuses. And perhaps in the background you can hear the baby nightmare that is currently happening. So, spectator ions, it's not manganese and it's not phosphate because those two combine to make a solid precipitate. The sulfate, however, is out, and the lithium is out as well. These are lousy, no good spectators that just hang out and do nothing. Like some high schoolers, actually. There you go. So whatever's left over is our net ionic equation. The ions that are aqueous to start, that form ultimately a solid product. Okay. Last example, one more single replacement reaction. This one is a non-metal replacement. We've got fluorine, which can definitely kick out oxygen. This is ammonium, by the way. Kind of got butchered, but that's okay. So we're going to produce ammonium fluoride, so NH4F, and then we'll kick out oxygen, which is diatomic, so O2. Alright, so if that is doubled, then we'll need to double this. And that gives us 4 ammoniums, which means I need 4 of these and 2 of those. Okay, now I'm going to go back and evaluate solubility. Don't need to think about it for my 2 diatomics. Those are going to be gases. Okay, ammonium oxide. Oxides are usually insoluble. Ammonium, however, is an always is. Okay, so this is aqueous, and here's my always is again, so also aqueous. Okay, so I'm going to take this and I'm going to make a total ionic equation. Remember, the only thing that changes when you go from the reaction to the total ionic is anything that's aqueous. So this is going to stay the same, this is going to stay the same, these two are going to get blown up into their ions. So we've got 2 fluorine gases. I'm going to have 4 NH4 1+ ions that are aqueous. I'm going to have 2 oxide ions that are also aqueous. Notice I didn't write O2 because this is an ion, it's part of a compound. And then here on my product side, here's another 4 ammoniums. And now I've got 4 fluorides. Oops. Dang it. That says 4F1- that are aqueous, and then oxygen gas. Okay, so let's find our spectator. Nope, just spectator. It is not fluorine. Okay, Now you might be thinking, it looks like it's not part of a compound on either side, so it should be a spectator. Guys, this is different. Here, this is molecular fluorine. On the product side, it is fluoride the ion, all right? It has gained electrons. It has been reduced, is the technical term. It goes through a chemical change. It is not a spectator. Same thing with oxygen. Oxygen goes through the reverse process. Here it is oxide. We have two oxide ions that are dissolved in water, and then they are oxidized, go figure, and form oxygen, molecular oxygen gas. Okay, those are not spectators. The only spectator here is ammonium, which starts as an ion and ends as an ion. So I'm going to get rid of those guys. And that which is left over is my net ionic equation. So 2 molecular fluorines plus 2 oxide ions react and form 4 fluoride ions and then just 1 molecular oxygen gas.